Okay, so let's resume the class. Okay, so today we will talk about. Okay. So today we will talk about an application of group. So we are going to talk about something called a group code. Okay. So what is a group code? Okay, so group code is a special form, a special case of something that we call it a block code. Okay. And then what is a block code? Okay. So a block code is to assume that, so we want to transmit some message. Let's say this is some Alice. This is some Alice. And then let's say this is a Bob. And let's say this is a channel that they want to do the transmission. And this channel may be a bit noisy. So that during the transmission, error may happen. Okay, so we want to do some transmission between Alice and Bob, such that if there is not much error during this transmission, then whatever Alice sends to Bob, Bob can understand, can decode back originally what Alice has sent. Okay, so this is the purpose of having a code in our scenario here. So there are different kinds of codes. Some code aims at minimizing the total number of bits, so this is called a compression code. But here, this is called error correcting or error detecting code. So we want to make sure that Bob knows whether anything has happened to the message sent. Is it going to be wrong or is it going to be very wrong? Okay. So block code has a property. Okay. So each message that Alice is going to send is of fixed length. Okay. So let's say this is going to be a 5-bit string for the first code, and then the second one is also a 5-bit string of the second code. Is that okay? So all the way they are of the same number of bits. So n bits, n bits, n bits, n bits. Each one of them, we call this a code word. Okay. 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 So first of all, to understand block code, we have what? We want to define something called a distance between two words. Okay. So let's say we have a distance function between two words. Let's say we are looking at 101. So this is some n-bit string. Let's say we have something like 0, 1, 1, 0, 0. So this is going to be equal to, we define it to be the Hamming distance of them. So the distance is going to be the Hamming distance between them. So 1, 0, 1, 0, 0, 0, 1, 1, 0, 0. And then it is exactly the number of positions that they are different. So if you look at it, the first position, 1 is 0, the other is 1. So position 1 is different. Position 2 is also different. But position 3, position 4, position 5, they are the same. So the distance is going to be equal to 2. Is that okay? Is that okay? Okay. Now, and then what is a group code? A group code has a special property that all the code words. So if you look at the set of the code words, and this exclusive or operator, it forms a group. Okay? It forms a group. So I will have an example for you. So let's look at this example. So for instance, let's look at this case. So we have 0, 0, 0, 0, 0. This is the first one. We have 0, 0, 1, 1, 1. This is the second one. We have 1, 1, 0, 1, 0. This is the third one. and we have 1, 1, 1, 0, 1. This is the fourth one. Okay? Okay? So this is a finite. So we want to check whether this is going to give a group under this exclusive or bitwise exclusive or operation. So how do we check? So this is a finite group. Okay. And then this is a subgroup of all the 5-bit strings with this operator. Okay. To check what, so subset. Okay, this one is a subset. So to check whether this is going to form a group, we just need to check whether it is going to be a closed operation on this operator. Is that okay? So this one excluded or this one is this one. Is that okay? This is the identity. So identity doing anything with the other, it doesn't make any problem. So we just need to take a look of this one. This one exclusive for itself, it becomes the identity. This one exclusive or this one, you will see this is going to be this one. Is that okay? Is that okay? And this one exclusive of this one, you should get back to this one. Am I correct? It looks, is that okay? So this one is okay. So how about this one? This one exclusive of itself is going to be the identity. This one exclusive of this one, you get this one. This one exclusive of this one, you get this one. Is that okay? So this is also okay. For this one exclusive itself is the identity. This one exclusive of this one is this one. This one exclusive of this one is equal to this one. Okay, so this is a closed operation. So in that case, this is a group. Okay. Okay, so a group code will use this one, this one, this one, this one as the only code words for the transmission. Okay, so if I want to transmit, I may be transmitting 0, 0, 0, 0, 0. I may be transmitting this, or I may be transmitting 0, 0, 1, 1, 1. I may be transmitting 1, 1, 0, 1, 0, or I may be transmitting 1, 1, 1, 0, 1. Is that okay? Okay, let's take a look of the distance between them. Let's take a look of the distance between them. So what is the distance between this one and this one? What is the distance? 3. Okay. How about this one and this one? This one and this one, how many? 1, 2, 3, 4. Am I correct? 4. This is going to be 4. This one and this one, how many? 3. Is it okay? This one, how many? Just count the number of ones here. 4. This one and this one, how many? 3. Is that okay? And then how about this one, this one? This one and this one, 3. Is that okay? Is that okay? So the distance between any pair of them is at least 3. It's at least 3. So in other words, then what does that mean? If the transmission has no error, then of course we don't have any problem to decode the thing. If the transmission has 1 bit error, then it's good. Because this is 1 bit error. Let's say 1 bit error. So let's say this one, you transmit it to become 0, 0, 0, 0, 1. Okay. Then, so let's say we have something that is transmitted 0, 0, 0, 0, 1. Then the distance of this one is 1. And then the distance for this one to the other 3 one will be greater than 1. Is that okay? Okay. The reason is that I didn't show, I have omitted it here. The reason is that the Hamming distance function is a metric. So it follows the triangle inequality. So the distance from A to B must be shorter than the distance from A to C plus C to B. Okay, so if this one and this one has distance 3, this one has 1, then this one you must have things greater than or equal to 2. Okay, because it is already 3. It follows this triangle inequality. Is that okay? So here, this is a group code, and this group code can correct any 1 bit error. If you have 1 bit error at any location, for instance, this is 11010, right? So if I have 1 bit error at the second position during the transmission, so I'm transmitting 1, 0, 0, 1, 0. So the distance between this one is 1. Is that okay? But then the distance for this one to the other all three will be greater than 1. At least 2. Okay, so in that case, whenever there is just 1 bit error, we can use this group code to correct it. Okay? Okay. So we have this corollary. So we have this corollary. So suppose that, or this theorem. So let this G and this one be a group code. If the minimum distance between any distinct A, B in G is some number 2t plus is at least then this code can correct T errors, or can correct up to. Does this make sense? If the distance between any two of them is very far away, 2t plus 1, then if they are less than, if they are up to t errors, then that means that this one will be of a distance less than or equal to t to one of the code word. And the transmitter thing must be far away, at least t plus 1 or more away from all the other possible code words. So that means that we can find out what was already sent at the beginning. Is that okay? So in our example, 2t plus 1 is equal to 3. So if it has one error, then you can find the closest one to correct it, and then we are sure that all the remaining ones will be far away. So there is no way to decode ambiguously. Is that okay? If you're okay with this, could you please raise your hand? Okay, good, excellent. So that means what? That means that some group codes are good, some group codes are bad. The group codes that are good is to have what? Have the minimum distance between any pair of code words to be far away. Is that okay? So I can have a group code like this. So I can have a group code like 0, 0, 0, 0, 0, and then 0, 0, 0, 0, 1. And then a group code 0, 0, 0, 1, 0. And so I can have another group code. So let's say this is a group code. Let's say this is another group code. Okay, this is another group code. This is another group code. Because this one exclusive of this one, you get this one. This one exclusive of this one, you get this one. Is that okay? This is a group, right? But this is bad. This is bad. If this one has an error at the last position, then you don't know whether it is sending from this one or you are sending from this one. Is that okay? It may be you are sending from this one with one error, or maybe you are sending from this one with no error. Is that okay? So in this case, this is a bad group code. Okay? If you want a group code to be good, we need to make sure that the distance between any two pairs have to be far away. Is that okay? Okay, so let's get back to our original group code. So here, 1, 1, 1. 1, 1, 0, 1, 0. 11101. Okay. Okay, but here it may be a bit tedious. Okay, we want to find out what is the minimum distance between any pairs, any two code words in G. Okay, so that means if G has many things, let's say it has 16 things, we need to calculate 16 pairs, right? So it takes the size of G squared, number of cases, right? But there is a much better way. So as long as it is a group code, then there is a very easy way to find out what is the minimum distance. Okay, the minimum distance is we calculate what is the minimum distance of each of this one, each of the non-zero code word to the identity. So this one is having distance 3, this one has distance 3, and this one has distance 4. Okay, so the minimum of them will be the minimum distance. Okay, why? 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 The proof is actually easy. Okay, proof. So let's suppose that X in G attains a minimum distance with the identity, the code word 0. Okay, so let's call it this one. Okay, now for any y z in G, the distance of y and G, y and z, will be equal to the Hamming distance of y and z, because this is how we define. Is that okay? So this is equal to, so Hamming distance, you count what? You count how many bit difference are there between y exclusive of z in the word y exclusive of z. So it is equal to the number of ones in y exclusive of z. Is that okay? So this is what? This is the distance between 0 and y exclusive of z. Is that okay? Is that okay? Okay. So this distance must be, because x achieves a minimum distance, so it must be greater than the distance of 0 x by definition of x. Okay? So that means what? For any code word that you take it out, the exclusive or will contain at least the number of at least more ones than what x has. Okay, but on the other hand, x is one of the code in the code in this set of code words. So this one, so everyone has distance greater than or equal to x, and x has distance equal to the distance of x. So that means what? The minimum distance must be the same as the distance of x with 0. Is that okay? So we don't need to do all the pairwise comparison. We just need to find out, okay, how many ones are there? How many ones are there? How many ones are there? Okay, there are 3 ones. There are 3 ones. There are 4 ones. Okay, so we know that any pair, you must have distance at least greater than or equal to 3. Okay, so this is it. Okay, so this is the group code. And then, and then that's it. So the decoding using a group code is also very easy. It's also very easy. Okay. So here, it is correcting up to t errors. Is that okay? But how about detect? So in some case, we may detect an error, although we don't know how to correct it. So we know that something must be wrong because it is not one of the code words that we are sending. But we can still detect it. So for instance, let's say we are sending something like 10001. Okay, let's say we are sending this one. Okay. So this is not one of the. It is not any of the code word in our so-called G, in the code book G. It's not the first one. It's not the second one. It's not the third one. It's not the fourth one. It's not. Okay. On the other hand, this one has distance 2 from this one. This one has distance how many? 1, 2, 3 from this one. Okay, so let's take a look of the distance. So this one has distance 2 from this one. This one has distance 3 from this one. Is that okay? This one has distance 1, 2, 3 from this one, and this one has distance 2 from this one. Is that okay? 2 from this one. So in that sense, this one and this one are of equal distance to this one. We know that something is wrong, but we cannot find out where is the wrong place. So here in this case, so when let's say there are 2t plus 1 errors, when the distance is 2t plus 1 at least, then that means that we can correct up to t errors, and then we can detect up to how many errors? Up to t plus 1 errors. Is that okay in this particular case? Is it? Well, we need to check. Okay, so this is, okay, correct is correct. Okay, but detect, we need to find out. Okay, okay. So given a particular code word set, so we can construct. So here, this is a set that can, so here, in this example, this is a set that can correct up to 1 error. Is that okay? Up to 1 error. So we can write down a so-called decoding table, okay, like this. So we have G. So we have G, which is 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, and then 1, 1, 0, 1, 0, and then 1, 1, 1, 0, 1. So here, if we see any of these 4 are transmitted, then we will decode them accordingly. Okay, assuming that there are going to be no errors. But then what will happen? So let's look at this coset of G. This is going to give us a set of 4 different things, 4 different bit strings, which is applying this one to this one, this one to this one, this one to this one, this one to this one on the right. So we will have 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, 0. So if we see any of these 4, we will assume that there is an error in the last bit, and then we will correct accordingly to that one. Okay, so we will also see, so we will look at another coset. So this is going to be about the error at the second last position, and then we will look at a coset of this one, and then we will look at a coset of and then we will look at the coset of, is that okay? Okay. So if a string, a 5-bit string, belongs in one of these 6 cosets, then they can be uniquely decoded back to the original one. And then there are actually 2 more cosets. That covers the remaining strings. So if a string belongs to any one of these cosets, then we cannot decode them uniquely. not able to decode back. Uniquely. Okay, so that's it. Okay. Okay, that's it. Okay, so this is one of the application of group. Okay, but of course there are. So this is only one of the many choices of error correcting codes. So if you are interested in this topic, yeah, go to the web and check. So there are Hamming code that we have talked about earlier. There are also what? There are also Golay code. There are also Reed-Solomon code. There are lots of codes that can do the same purpose. All have different kinds of trade-off, and they will be using some linear algebra techniques to help. Okay, okay. Just as a side problem. Okay. Okay. So suppose that. Okay. So about twist of the IQ puzzle I've mentioned. Suppose that we now have five people. Each one is given a hat, black or white randomly, and then they need to win a game if every one of them can correctly is it? Yeah, let's say every one of them can correctly guess the hat of themselves. Okay. Okay. Is there a way that we can do so? That has, let me see. Does that make sense? Let me see. Never mind. I'll construct the game later. Okay. So that's it. That's all. So let's end the class early today. So that's all that I want to talk about. On Thursday, we still have one more class. So it will be about the tutorial on the assignment 5. Okay. Please come and then yeah. Thanks. Okay. Okay. We will have our exam next week. Yeah. That's it.